There we go. We're in module 2. Don't complete anything in here until I give you a heads up. But this is what module 2 looks like.
I
So
don't know why
I
she's
have
doing that.
already
I think Chris, you
presented
should read
some
this one so
PowerPoint
she can
lectures.
try to.
Now what you'll notice is when I was starting out creating these lectures, playing around with this screencast tool. And so you'll notice that, it takes about 26 seconds before that video plays. I got the hang of it a little bit later, but just be patient with a couple of these videos, okay? So there's only one lecture for chapter 2, and then there are 4 short videos for chapter 3 here, okay? 4 short videos here. Under video lectures is where you're going to find all of the lectures. So what are we supposed to be doing? So when it comes to your objectives, they're posted here. Okay, I'm going to turn on light, but these are the objectives. And I know it seems like a lot. There we go. I know it seems like a lot. But when I walk you through it, you're not going to even realize that we've covered those learning objectives. Okay. But chapter 2, it's not really in depth. It goes over some basics about chemistry, especially helping us to understand at those lower levels of hierarchy, those subatomic particles or atomic particles, right? Understanding our molecules. That's what we're doing. And then we're going to get into chapter 3, which is one of my favorite chapters, and it covers properties of water. Okay, it covers properties of water. Okay, so if you keep going, you'll see the PowerPoints here. There's some problem sets here. The things I don't want you to work on is, maybe I have some quizzes or things that are in here. I don't want you to work on those. All I want you to do right now is work through the PowerPoints, okay? Work through these PowerPoints, okay? Is that clear?
Yes, ma'am.
All right, so let's click on this one. All right, let me stop sharing my screen. Oh, I canceled. So whenever you're taking quizzes or exams, you can't take any. There are no notes. You can't use notes, okay? Unless, I give you notice and say, hey, it's okay to do X, Y, and Z. All right, so let's rock and roll. Take good notes today. Take good notes today. It'll be an assignment that I post. I'm going to post an assignment that says, show me your notes. Okay? Handwritten notes. I want to see it. I want to see it. All right. Let's rock and roll. So chapter 2, let's record. I'm not gonna record because I already have some videos in there that you can use. Okay. Once again, I cannot see the chat from this view. So post your questions and I will come back to those questions. Now, can everybody hear me clearly before I start? Can you hear me clearly?
Yes.
All right, let's go. Chemical context of life. So you guys had an assignment this past week, right? And it was due this week, and it was related to the hierarchy of life, okay? So when we look at this diagram, I want one person who completed the assignment who really thinks that they get it. They understand the hierarchy of life, and they can talk about it using this diagram. Somebody, let's see who's here. Somebody raise your hand who can take me through this diagram and explain it to the class. Crickets? Okay, I'll
I have
just
a
call.
question. When you say explain it, are you meaning like talking through like the levels of it?
Yes,
I could try.
that's all I ask, is that you try. Okay, go for it.
So basically, excuse me,
Who's talking to me?
this is Oriana Gordon.
All right, Oriana, let's go.
Okay, you want me to start from top to bottom or bottom to top?
Your choice.
Okay, so basically in this diagram is basically showing just the biological components uh of what it takes, I guess, to have like to look at an organism in totality. So if you go down to the bottom, it talks about atoms, and atoms are there's not the lowest level. Um, well, I take that back. Well, I think atoms are the lowest level, but subatomic particles are the lowest level. I'm sorry, but once you get past this part, which we get to molecular structure, like get into molecular structure, would be like atoms and molecule DNA. Then that's when we move into cell organelles, and then, of course, organelles are the little things within the cells that actually help the cells do their function. And that would be vacuoles and ribosomes and, Golgi apparatus, things like that. And so organelles, including the nucleus, of course, because that holds the DNA to the organism itself. So once we get past the organelles, we get into the cell itself. And cells are basically the smallest functioning units of life that help things do their function. So depending on the cells come together to make tissues, and tissues are just groups of two or more cells that function together to get another job done. And so once we progress from tissues, we get into organs, and organs are almost like a bigger cell. And I say that like metaphorically, right? Where organs have their own functions as well, depending on what organ that you talk about. Of course, its function based on like its name, and right here it's talking about the brain, where it says organ brain. And so, of course, the brain is responsible for all responses that basically happen within the body. They regulate everything, well, at least for humans, at least. Everything is regulated from the brain. So once we progress from the organ, we get into the organ system, which is a group of organs that's designed to help the body like work its processes. So there are different organ systems, of course, like respiratory, digestive, and things like that. But in this diagram is listed is the nervous system. And of course, we all know that the nervous system, we have what voluntary and involuntary movements. And the nervous system, of course, like the spinal cord and the brain that's attached to it, that's the central part of the nervous system, because everything is controlled from the brain heading down. And the bigger part of the organ system, all of these things come together to create the organism. And in this diagram, there's the brown pelican, and it just kind of shows that the nerves that go through the pelican, that's all connected to the brain, because that's what controls it. And that's what I saw in this diagram.
Yeah.
You better work. I'm gonna turn on my camera and I'm gonna give you a high five. You gotta turn on your camera and give me a high five because you put in work.
And I
We're
go put on a hat real quick.
okay, okay, but high five in the air then because
High
that
five in the air.
that was awesome. That was really good. Impressive.
No, no, it's
Really,
fine.
really
It's
good.
fine.
Good job. Good job. Okay. Very good job. All right. That's what I'm talking about. All right. Good job. Any questions when it comes to this? Anybody have any questions? I think she did an excellent job. You guys give her a shout out. She did a really good job. And whatever, a clap or something. That was really good. Okay. So now, if you think about what Oriana shared with us in terms of this lowest level, right? So the lowest level is the subatomic particles. So give me some examples of subatomic particles.
Protons.
Uh-huh.
A neutron, electron.
Good. Protons, neutrons, electrons, okay? And then we move up to the atom, right? And then we talk about elements and so chemistry. The chemistry of life is what this chapter is about. I know we teach you chemistry in a different, a whole different course about chemistry. Then we teach you biochemistry, where we put biology and chemistry together. Okay? But the reality is that all of these subjects they come together, especially when it comes to living organisms. So when you think about chemicals, light energy, chemical energy, right? There are different chemicals within, you think about water and what it's composed of, the elements that are there, right? So the plants themselves take chemicals from the soil and chemicals from the air, right? The chemicals are going to go into this caterpillar, right? Whenever it eats the plants and whenever we consume things, okay? So the chemistry of life is critical. So what does life really depend on? What does it truly depend on to exist? Okay, what do we need to exist? I want you to be thinking about a water strider. These are what we call the Jesus spiders. And they literally walk on water. It's not like pretending. It looks like, no, they do. Okay. How is it possible? How is it possible that a bat can navigate its way through a cave and stay warm at night? How does a bumblebee actually fly? How does a gecko really walk on the ceiling? How can a tree get water from the roots up to the highest leaves? How do the nutrients that we consume, how do they get through every one of the cell membranes that we have in our body? It's because of chemistry. This is a gecko, and the ability of the gecko to, adhere, if you will, to glass. Not magic, it's chemistry. Okay? We always say biology is a study of life, and it is. But the part that I want you to get from this is that when it comes to life, living organisms and the environments, they're subject to these laws of physics, subject to laws of chemistry. This is the chemical formula for formic acid. Okay, you can see all the bonds that are here. Formic acid. Why do we care? How does that apply to life? Formic acid is what these ants use to protect themselves against predators, and how they protect themselves against microbial parasites. And this is its chemical structure. Okay? What is matter? This is something that you learn from elementary school. Matter is anything that takes up space and has a mass. Okay? So when we go into this concept about chemistry of life, you have to understand it from the basics. That all organisms are made of matter. You're made of matter. And then matter is made up of elements. When did you hear about elements? In chemistry class. So what's the difference between an element and a compound? An element is in its most simplest form. This is sodium. Look how soft it is when they cut it. This is chlorine. So when the chemistry, the bonds come together to make sodium chloride, it changes its structure. And this is table salt. So whenever you're using table salt or seasoning today, I want you to say sodium chloride. Don't say salt. Get it in your head. Use these terms on a day-to-day basis. You're taking sodium and chlorine, not you, but the company took sodium and chlorine to make sodium chloride. So what is an element? It's a substance that cannot be broken down to any other substance. So give me some names of some elements in the chat. In the chat, post some elements. Talk to me about some elements. Everybody should put something in there. Gold, zinc, come on, iron, neon, let's go. Aluminum, come on, everybody should be giving me at least one element. Hydrogen, carbon, magnesium, good, let's go. Beryllium, oxygen, bromine, let's go. Potassium, carbon, come on, give me something. Boron, everyone needs to post. Barium, argon, think about those inert, right? Those inert gases over there that you had to learn. Silver. Okay, all of these are elements. Okay, and then let me move the chat out of the way. Give me a second. And then compound. So give me some compounds. So you're giving me elements. Okay, so give me some compounds. Magnesium chloride, carbon dioxide, water. Give me compounds. Good. Potassium nitrate. So a compound is a substance that has two or more elements in a fixed ratio. A compound has characteristics different from those of its elements. Does that make sense? So an element, sodium, and then we have chlorine. Those elements, their characteristics are different than sodium chloride. Does that make sense to everyone? And then you already named elements, okay? What else do you need to know? So here on this table, I'm showing you different elements, okay? I'm showing you their symbol, And I'm also sharing with you that within the human body, okay, let me move this out of the way. Within the human body, we have these elements, okay? Now, some of them are trace elements. This is a question that we ask all the time. Some of them are trace elements. You guys see me circling trace elements?
Yes, ma'am.
All right, excellent. So some of them are trace elements. Now, what do we mean by trace, right? If you trace something, you know how when people were in kindergarten, they had to trace lines, right? They had to go to follow the line, trace. Very small. They had to make these small, subtle changes. So trace elements are those elements that represent less than 0.1% of our body mass. Less than 0.1% of our body mass. We have trace elements. Okay, there are a lot of elements in our body. Our body mass, the percent of our body mass, you see here. Let me, can you guys see this point, this pen circling around?
Yes.
Yes.
All right, so I'm gonna use this as a pointer, okay? So in your body, okay, the elements that make up the majority of your body mass is what we call CHON. That's what I said, CHON. What is CHON? That is carbon, hydrogen, oxygen, and nitrogen. Carbon, hydrogen, oxygen, nitrogen. So the largest percentage of body mass is composed of those four elements. 96.3% of your body mass is composed of what four elements?
Oxygen, carbon, hydrogen, and nitrogen.
Yep. 96.3% of your body mass is mainly composed of what four elements? I only heard one person talking to me.
Carbon, hydrogen, oxygen, nitrogen.
Yes. So that must mean, right, if the total is 100%, where's the rest coming from? Right? Where's the rest coming from? So there's a small percent that you see here with the other elements within our body. But then we have trace elements like boron, chromium, cobalt, copper, fluorine, iodine, iron, magnesium, molybdenum, selenium, silicon, tin, vanadium, and zinc. Okay? And I'm going to highlight iodine. I'm going to put an asterisk by iodine. Talk about iron. Just a little bit. Selenium. So these are these trace elements, right? We're finding more and more in science that these trace elements, although they represent less than 0.01% of our body mass, when they're not present, some things go awry. Okay? Sometimes people have a little bit of dementia. If there's really low levels of selenium in the body, it's amazing. Iron deficiencies. A lot of people have iron deficiencies, right? And so the iron deficiency, it impacts how your body carries oxygen. People get tired when they have iron deficiency, okay? And then I'm going to highlight iodine. So we talked about the elements in the human body, and I want you to know this right here is going to be very important, okay? The CHON is very important, okay? So 92 elements are essential to life. Of all the elements that you had to learn when you were in chemistry, there are 92 of them are essential to life. Of those that we've discussed, carbon, hydrogen, oxygen, and nitrogen make up 90% of living matter. I mentioned to you trace elements. Okay, now what are those trace elements? Let me go back and make sure. Yeah, we just talked about these trace elements, right? Give me 3 trace elements. Give me 3 trace elements in the chat. Give me 3 trace elements. You just saw it. You should have memorized a few. 3 trace elements. If those that are required by an organism, but only in minute quantities. Iron, I talked about iron. Selenium, boron, cobalt, okay? Zinc. You know how now people are taking that zinc, right, during the pandemic? Zinc is playing a role in immunity. Okay, good. So what is a trace element? What is a trace element? Okay, I'm going to underline it here. Trace elements are those elements that are required required by an organism, but you only need them in minute quantities, small quantities. Okay? Trace elements are required by an organism, but only in minute quantities. The body needs the carbon, hydrogen, and oxygen. Okay? But it also needs these trace elements, but it doesn't need as much. Okay? So what we have here is a person who has an enlarged thyroid. Okay? An enlarged thyroid gland. And it's called a goiter. Let's go back. A goiter. Now the question is, why do goiters come about? Why do they exist? This represents a deficiency in iodine. Like, there are other reasons, but that's one of the reasons why people have goiters. Iodine deficiency. And so how do you get iodine? Where do we get iodine from in our food? Why do you not see a lot of people now walking around with goiters? What changed? Anybody know? Where do we find iodine now?
Can't you get like iron pills or iron vitamins now?
No, that's iron. That's different. Iron is IRON. I'm asking about iodine.
Salt.
There you go. Sodium chloride. So we have this iodized salt. You guys know, if you look on your salt shakers, iodized salt. That is salt that has iodine in it. Fish. There are fish that has it in it. Okay? So now we can get this iodine into our diets. Okay? A lot of people have moved away from iodized salt and moving into sea salt or pink salt. But we need that iodine. Okay, so incorporate a little bit of that iodine. You don't need a lot, because it's what type of element?
A trace.
Trace.
Yes, work. All right, so elements. We talked about essential elements, and we talked about trace elements. Okay, we compared essential to trace elements. Okay, we talked about the difference between an element and a compound. So now we're going to talk about the properties of atoms. We're going to talk about properties. So every element has unique atoms, right? Its atoms are arranged in a unique way. Okay? Atoms have these subatomic particles. What are they? Neutrons, protons, and electrons. Your neutrons are neutral, no electrical charge. Your protons positively charged, electrons negatively charged. And I know you've already heard all of this. Okay, so that's why I said it doesn't take us long to get through these chapters. All right, so if you're looking at your screen, you see an atom here, and you see the subatomic particles here. Now, in some of the videos that I have on Blackboard, I'm going to show you how, these electrons are free floating around in space. So we always show you pictures, right? And so it looks like this. You think it in your head that this way, but it doesn't. These electrons are spinning around and moving around the atom. Okay? They're moving around the atom. They're being pulled, closer to the protons, right? There's an attraction there. Okay. All right. So what you're seeing in the nucleus, right? Cells have nucleus. Guess what? An atom does too. It's the centralmost part of an atom. What do you find here? You see neutrons that have no charge, and you see protons. Your electrons, you notice, they form this cloud, this negative cloud around the atom, and they determine the chemical behavior of the atom. I need you to know this. Okay, I'm going to highlight that. I need you to know this. But Dr. Bradford, what don't you need us to know? I know everything. I want you to know it all. Your electrons are forming a negative cloud around the atom, and they determine the chemical behavior, how it behaves. How it behaves. What else do you need to know? I need you to know that neutrons determine the isotope. Neutrons determine isotopes. Protons determine elements. Electrons determine the chemical behavior. Protons tell you about the element. The neutrons determine the isotope. What do you mean? So when we're looking at all of these elements, right, and the atoms of the elements differ in how many subatomic particles are present, the number of subatomic particles. So the atomic number is the number of protons in the nucleus. The atomic number, atomic number, is the number of protons in the nucleus. Can you all still hear me? I see a few hands popping up. I want to make sure you can still hear me and see the screen.
Yes,
ma'am.
yes. I
Okay,
was trying to.
get to your questions. I'm gonna get to your questions in a minute. I'm gonna finish this one. I'm gonna answer your questions. Okay. So think about the atomic number. I want you to know it's the number of protons in the nucleus. Mass number, mass, the sum of the protons and neutrons. Okay. Atomic number is just the protons in the nucleus. Mass is the protons and the neutrons. Okay, the mass number. But then you also see atomic mass. So what is the atom's total mass? So if you approximate the mass number, you get the atomic mass. Okay, go ahead. Let me see. The raised hands disappeared. I can't see them anymore. Oh, there we are. Okay, Gordon had a hand raised.
Oh, yes, ma'am. I wanted to know, could you go back to that part about what the protons and electrons do again?
Uh-oh. Okay, so our protons, here we go, positive charge. Okay. Electrons carry a have a negative charge. And so they form this negative cloud around the atom. And they determine the behavior, the chemical behavior. And this is what I want to highlight. We're going to getting ready to jump into the isotope. But I want to really highlight, I want you to understand, electrons determine what? What do electrons determine? Put it in the chat.
Chemical behavior.
The chemical behavior of this atom. How this atom behaves is determined by the electrons. Okay? Now, you're going to have to identify isotopes. Isotopes are crucial and critical to life. Okay, why are they important? Why are isotopes important? What are they and why are they important? Okay, so the atoms of the elements. So we just talked about elements, right? Carbon, hydrogen, oxygen, nitrogen, sodium, chlorine. We talked about these elements. Okay, so when it comes to the atoms in the element, they have the same number of protons, right? So you have an atom. You might have a carbon atom, two different carbon atoms, okay? They may have the same number of protons, but they're going to have different neutrons. And if the neutrons differ, you can see it. They're called isotopes, okay? Isotopes are two atoms of an element. They have different number of neutrons. And I'm going to show you what I mean, okay? Why does this matter? So whenever you're studying, when people are studying evolution, or you're just studying history, okay, you try to date things, and they use isotopes to date things. Isotopes give off, when they decay, they give off particles and energy, and you can measure that. The other importance of radioactive isotopes is that these isotopes are utilized to tell if someone has a tumor or a cancer. Okay, because you can have the patient you can inject a radioactive dye into the patient, and by knowing how isotopes work, they should only show up where there is life. Okay, giving off particles and energy. As soon as things are dividing, they're showing up, and then it's like, oh goodness, it shouldn't be here. Okay. So radioactive isotopes are used as diagnostic tools. We can use them to track atoms that are going through metabolism. Okay? So here's an example of cancerous throat tissue where someone has been given a radioactive dye, and that dye is utilized to detect the cancer in the throat of this patient. Okay? Because that radioactive isotope, every time the cell is going through metabolism, it gives off energy. And you can see it there. Okay. So a minute ago, I shared with you, when we look at an atom, we can see the nucleus. And in the nucleus of the atom, there are two things that show up. What are they? Put it in the chat. What are those two things that show up in the nucleus of an atom? Okay, protons, not electrons. Protons and neutrons. Protons and neutrons, not electrons. Protons and neutrons show up in the nucleus. Now, surrounding the atom is a cloud of negative energy. Negative, giving off this negative energy. That negative energy is in the form of electrons. Now, these electrons determine what about the atom? The electrons tell you what about the atom?
Chemical behavior.
All day. The electrons tell you the chemical behavior. The neutrons tell you if it's an isotope or not. Okay? The electrons tell you the chemical behavior. The neutrons tell you if it's an isotope. Okay? When we look at the periodic table, we look at the electrons and how they're distributed. The electron distribution. So if we look at these periodic table, you see with hydrogen, there's one electron, that negative energy, floating around, right? That in the cloud, we see helium has 2 electrons, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Look at these. So in their first energy shell, right, is complete when they're 2. In the second energy shell, you see 1 for lithium. You see 1 in this third shell for sodium, right? So that is one way that you can pay attention and quickly figure out how many electrons are in the outermost shell of this element. Okay, if they're in the same column, they have some similar behavior. Behavior is determined by the electrons, chemical behavior. So hydrogen has 1, lithium has 1, sodium has 1. One what? 1 electron in the outermost shell. Dana Dozier, how many electrons are in boron's outermost shell? Dana Dozier? Can you hear me? Amaya Champion, how many electrons are in carbon's outermost shell?
6.
Nope.
Oh, 4.
Thank you. 1, 2, 3, 4. Courtney Dunlap, how many electrons are in oxygen's outermost shell?
Six.
1, 2, 3, 4, 5, 6. Corey Smith, how many electrons are in sulfur's outermost shell? Notice it's in the same column with oxygen.
6.
6. You don't even have to count because it's in the same column. You need to pay attention though, because some people don't create their periodic tables the same. So sometimes you have to pay attention. Okay. All right. What else? Who else is on this list? Let's see. Jacob Grant. Can you hear me?
Yes, ma'am.
Okay. Argon has how many electrons in the outermost shell? Argon. 8. So it's over here in this column, right? And so all of the majority of these over here in this column, we consider inert gases, which means they really don't, there's no impact on behavior because they have complete outer shells, right? 8. Helium has a complete shell too. It just has 2. Everybody agree? 2, 4, 6, 8. These electrons in this outermost shell Brooklyn, what do they determine? The electrons in the outermost shell, they tell you something about the atom. What do they tell you? Gerald, the electrons in the outermost shell tell you something about the atom. What is it?
I'm actually unsure about what it tells you.
Deanna? Rockmore? Antonio Yarborough?
The chemical behavior.
Thank you. All day. The chemical behavior. You guys, I just highlighted that. Remember? You got to pay attention. These electrons in the outermost shell determine the chemical behavior of the atom. Okay? Don't forget it. Now, you'll look at periodic tables and you'll see things like this and you'll see things like this. Okay? Now, if I were to ask you, what is the mass number? Okay? What is the mass number of helium? Not the atomic mass, the mass number. Or what if I ask you, what's the atomic number? Okay? I will give you a diagram like this, or I'll just give you this electron distribution diagram, and you should be able to tell me some information. Okay? So the atomic number is 2 for helium. Okay? The atomic mass is 4. Okay? This is the element symbol. This is the electron distribution diagram. So these are terms that I need you to know. Okay? So I say, okay, which of these is the symbol for helium? Which of these is the atomic number? And what does the atomic number tell you? What does the mass number tell you? Okay? Can you find the number of neutrons if I give you the atomic number and some other information? Okay? So what is H here? What is this?
The symbol for hydrogen.
The symbol for hydrogen. He is the symbol for helium. Okay? What are these down here? What are those? What are these?
Electron distribution diagrams.
Exactly. What are these?
Electron.
Electron.
What do electrons tell you?
Chemical behavior.
Yep. I was going to ask somebody who told me they couldn't tell me earlier. I can't find their name now. You were saved by the bell. All right, you guys, I love to talk, so y'all have to keep me on target with our time. How we doing? 10:27. Okay. All right, so we've already covered that. Oh, a term. All right, this is a term I need you all to know. Let's do magenta. Okay, valence. Okay, not valence, not, I don't know what else y'all come up with, but valence. All right, can we say valence?
Valence.
It's like V-A-Y. Valence. I don't know how to do lens. Valence. Okay? So these are valence electrons. Valence electrons. What are valence electrons? Valence electrons are those electrons in the outermost shell. Okay, Guadalupe, are you there?
Yes, ma'am.
Okay, how many valence electrons does neon have?
8.
8. How many valence electrons, Guadalupe, does argon have?
8.
8. And they're in the same column. All right. Let's see. Janiyah Jenkins. What does this 9 represent? Janiyah Jenkins.
Oh, I said the atomic number.
Okay. What does the atomic number tell us?
The amount of protons and electrons. And
Who?
the valence.
Let's go back. Atomic number is, are you seeing my screen?
Yeah, number of protons.
Just protons. Okay, but you're saying, hey, if you know the number of protons, you probably can figure out electrons, right? Is that where you were going?
Yes.
Okay, good. Okay. So the number of valence electrons, Guadalupe, in neon and argon were how many? Guadalupe?
8 and 9.
Not 9. How many valence electrons were in argon and neon?
8.
8. Okay. Valence electrons. What are they? What are those? Valence electrons are the electrons in the outermost shell, or we call it the valence shell. Now, these valence electrons, I'm getting you to work on your language of science. The valence electrons, they tell you something about the atom. What do they tell you, Yarborough?
Can you repeat what you said?
What? The valence electrons, they're these electrons in the outermost shell, correct?
Yes.
What do they tell you about the atom? What information do they give you?
The chemical behavior.
All day. They tell you the chemical behavior of that atom. Okay? If that valence shell is full, the chemical is inert. What does inert mean? Somebody talk to me. We're our chemists in the room. Neon is inert. What does that mean? Somebody look it up. I'll wait for you. Inert, the definition, give it to me. I'll type it in.
Lacking the ability or strength to move.
So that's probably the Webster's definition, right? What about a chemically inert atom? Look that up. It's going to be related, but it's going to be more specific.
Do not initiate a response or interact when introduced to a biological tissue.
Come through. No reaction. But you just said, Bradford, that the chemical behavior of an atom is determined by the electrons in the valence shell. So what I am sharing with you too is that if there are 8 or 2, like helium, then that valence shell is full. And so it cannot react, but the others do. Okay? Now the question is, how do they do that? So if an atom has an incomplete valence shell, incomplete. What does that mean, incomplete? If we're dealing with, let's go back. Okay, so if an atom has an incomplete valence shell, okay, Oriana Gordon, does nitrogen have an incomplete valence shell?
I'll say yes.
That's correct. Janaya Jenkins, does oxygen have an incomplete valence shell?
Yes.
Michaela Harper, does fluorine have an incomplete valence shell?
Yes.
Kelia Perkins, does neon have an incomplete valence shell? Kelia Perkins, does neon have an incomplete valence shell?
No.
Correct. Does that make sense, everybody? Notice how we worked our way to the right. And as we moved to the right, more and more electrons were being added. So nitrogen had 2, 3, 4, 5 in its valence shell. Oxygen had 2, 3, 4, 2, 4, 6 in its valence shell. Fluorine has 2, 4, 6, 7 in its valence shell. Neon has 8 in its valence shell. So the one out of these 4 that is inert, that does not react, is which one?
Neon.
Good. Yarborough, you had your hand raised?
No, that I just forgot to put it down.
Okay, good. All right, so I want y'all to get it. If an atom has an incomplete valence shell, guess what? It can share or transfer those electrons to other atoms. Okay? And when those interactions between atoms come together and there are bonds between them, the bonds are called chemical bonds. So when these atoms are interacting with one another, okay, and the interaction results in an atoms staying close together, they're held by these attractions called chemical bonds. Okay, now there are different types of chemical bonds. There's a covalent bond. Sharing is caring. Covalent bond is the sharing of a pair of valence electrons by two atoms. Okay, except when you're sharing viruses or something. I ain't got time for that. But we're going to share some other stuff. Okay, I don't know what I can share with you right now. I'm sharing some information. Okay, covalent bond is the sharing of a pair of valence electrons by two atoms. Now, in the covalent bond, the shared atoms count as part of each of the atoms' outermost shell. Remember, the electrons in the valence shell determine the chemical behavior of the atom. If we have a molecule like water, H2O, it has two or more atoms. It has hydrogen and oxygen. How many hydrogen atoms are in water molecule?
Two.
Two. How many oxygen?
One.
Okay. H2O. One oxygen molecule, two hydrogen molecules. Two atoms. Okay. No, three atoms. Okay. All right. Now, the bonds can be single bonds or they could be double bonds. Okay. So if it's a single bond, you're sharing one pair of electrons, valence electrons. If it's a double pair, they're sharing two pairs of valence electrons. Okay? Single bond, double bond. Single bond, single bond. Sharing one pair of valence electrons, sharing two. So when hydrogen comes together, two hydrogen atoms come together to form H2, right? They're sharing a single pair of valence electrons. Oxygen, on the other hand, remember, 2, 4, 6 valence electrons, and the other oxygen atom had 2, 4, 6. So to complete the valence shell, oxygen just needs 2 more valence electrons. And so it can bind with another oxygen molecule and they can share the electrons. And when they share two pair, you get a double bond. Water is that molecule that you're going to have to know that you know how to write it, how to draw it. We ask you all day, every day about this water molecule. Okay, you need to be able to do this. Then you need to be able to show me how these bonds form, and I'll tell you what we mean. So with water, H2O, 2 hydrogen, 1, 2, 1 oxygen. Okay, 2 hydrogen, 1 oxygen. Let's see if this will play for us.
A covalent bond is the sharing of a pair of outer shell electrons by two atoms. For example, each of these hydrogen atoms has one electron in its outer shell, but needs 2 electrons to complete its outer shell. If the 2 hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as 2 or more atoms held together by covalent bonds. An oxygen atom needs 2 electrons to complete its outer shell. 2 oxygen atoms can share 2 pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, 2 shared pairs of electrons. A carbon atom needs 4 electrons to complete its outer shell. It can share electrons with 4 hydrogen atoms, forming a methane molecule containing 4 single covalent bonds. Methane is a compound a substance formed by the combination of two or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs two additional electrons to fill its outer shell. Thus it can form two single covalent bonds. An oxygen atom can share electrons with two hydrogen atoms, forming a molecule of water containing two single covalent bonds.
Okay. Any question on this? Does this make sense to everyone? Can you hear it? Did you hear it?
Yes.
Okay.
A covalent.
All right, let's keep going. So covalent bonds are about sharing. Remember, sharing is caring. Covalent bonds are about sharing. We want to share just about everything, but there's some things we don't want to share. What do we not want to share? Put it in the chat. I know what I don't want to share. I'm going to put it in the chat. I am not sharing. I'm not sharing my toothbrush. I can't. I'm not doing that. Some people do it. No, not doing it. I'll give you some food, but you can't have my toothbrush. Bath towels. Yeah. Oh, yeah, underwear. That's a good one. Money. Okay, I'll share that. Yeah, underwear is a good one, though. Yeah. Pillow. Yeah. Car. Okay. So sharing is caring until we talk about some underwear and some other stuff. Okay. Covalent bonds is what is happening between the atoms? What are they doing between the atoms? What is happening? What's that word?
Sharing
They're sharing. What are they sharing?
electrons.
Electrons. Sharing is caring until it's, oh, your spouse. Good. Not doing it. Or your partner. All right. Now, this is our almost last topic, okay? When it comes to the chemistry of life. So the outermost shell of an electron is called the what shell? Blank shell. The outermost shell of the electron is called the what shell? Put it in the chat. The outermost shell. Yarborough, what is it?
Electrons?
Nope. The valence shell. The outermost shell of an atom is called the valence shell. That's where you find the valence electrons, correct? Okay. Now, atoms in a molecule, they can attract electrons to varying degrees. I want you to listen. Atoms in a molecule, think about hydrogen, that one atom. Think about oxygen, we're talking about those valence electrons, okay? Those 6 that are sitting out there. Those electrons can attract, those atoms can attract electrons at varying degrees, okay? Electronegativity. This is a word you need to write and know. I'm going to have you post, remember I said I'm going to have you post your notes from today as an assignment, okay? Electronegativity, what is that? That is an atom's attraction for the electrons in a covalent bond. So I always say, this is one of the ways that I teach electronegativity. It's attraction. Attraction. Electronegativity is an atom's attraction for the electrons in a covalent bond. So the more electronegative an atom is, the more strongly it's going to pull the shared electrons toward itself. I always say, if you pay attention to people, okay, think about freshmen all the way to senior, okay, there is things that change their electronegativity. People become more attractive sometimes over time, right? From freshman year to senior year. Sometimes there are people that you didn't see as attractive freshman year. Something changes, and then by junior, senior, they look like a totally different person. Their electronegativity changes. One of the things that I notice on campus is people began to join sororities and they joined fraternities. And always say, okay, maybe their electronegativity wasn't anything their freshman year, but once they join this fraternity, all of a sudden people start going around them. Their attraction changes. They become more attractive. And it may not be their physical attraction, but it's something that draws people to them. People become part of SGA and their electronegativity changes, okay? So I don't want you to forget that term. So today we talked about sharing, okay? And that was with covalent bonds. And we're going to talk about electronegativity, and that is the attraction, okay? Attraction. So this isn't the best diagram, but I love it because what it shares with you, what it shows you, is the electronegativity of the different elements. And you can see how it changes. See how these numbers change? So the more electronegative the element is, the more red it is. Okay, you see that here? So which of these elements are more electronegative when you look at this table? More electronegative. Which ones?
Fluorine.
Fluorine. Can you all see my pointer?
Yeah.
Okay. What else is more electronegative? Like, just look over this whole entire
Oxygen.
Oxygen.
oxygen. Okay. Let's look at lithium. Let's look over here on the left side. Sodium. Look at those. They have low electronegativity. So what is, I'm trying not to tell you the word. So they have low electronegativity. So if we say their electronegativity is low, what are we really saying?
They don't really attract to other elements, maybe? I don't know.
They don't attract.
They're easily pulled in to the stronger ones.
Oh, that's possible. You can say it that way. Okay. But they don't have that attraction. They don't pull. They don't have that pull. That's something we used to say back in the day. Oh, he has pull or she has pull. We say game now. Well, what else do y'all say? When you say that somebody can, they can attract people or something like that. What do you say nowadays? We used to say they have game or they have pull. What do you guys say? What's the term? No term? What? There's
a
some
term. I just don't think it's very appropriate.
Put it in the private chat to me, okay? I want to know. But anyway, there is
I think game is still used though a little bit.
Okay, so chlorine, fluorine, oxygen, they have game. They have more pull than, say, beryllium, magnesium, okay? And that electronegativity is really going to determine how they react with other electrons, so other atoms. All right, we have 3 minutes. So what I want you to do before we meet on Thursday is I want you to review all of the bonds. We talked about covalent bonds, but then there are 2 different types of covalent bonds. So I want you to review before we meet covalent bonds, ionic bonds. See here, covalent, ionic bonds, and I'm going to describe these things to you next time we meet. And I want you to be able to, okay, we have what we call van der Waals forces, van der Waals forces, okay, covalent bonds, ionic bonds, van der Waals forces. Yes, so this PowerPoint is there. I pulled this PowerPoint from Blackboard this morning. Okay, hydrogen bonds. So just look at all the bonds. Okay, and then you have a quiz on Thursday over chapter 1. Okay, everything that we covered in chapter 1. Not today's work, last week's work. Okay, so what are you reviewing tonight? Give me the bonds.
Covalent bonds.
Hydrogen, polar, non-polar.
Ionic.
Okay.
Hydrogen bond.
Yep. And one more.
I forgot the last one.
Van der Waals interaction.
Oh, that.
Okay. Van der Waals forces. Okay. I spelled wall wrong. It auto corrected me, but I put it in here. Okay. It's WAALS. All right. I think that's our time, y'all. Time flies when you're having fun. Take care of yourselves, guys. I really want y'all to be safe. Okay. Because I really do.
What are we turning in today?
Today you're going to do the notes that you took class today.
And you already have a section ready for that, or you have to make it?
Not yet. As soon as we finish, I'm going to put an assignment. Okay?
Okay.
I want you to post your notes. You're welcome. Post your notes from today's lecture. It should be handwritten.
We have until 11:09 to turn it in. If you want to go through the whole thing again.
Repeat that.
We have 11:59 to turn it in. If you want to go through for the notes.
I want your rough notes. I don't even want your detailed notes. It's just just an assignment to tell me that you were here and you were paying attention.
Okay.
Okay. I can stay on. If anybody need to talk to me, I can stay after, okay? I'll stay on. You guys have a good one.